Check, we're just about there, folks, just running the clock. Any questions while we're waiting? Well, I think we can start. Welcome back, folks. We're now in week 4 of 16. So that means we're like 25% done after this week is out. Congratulations on that. We're almost done with section 7.5, but probably the larger announcement is that we scroll down onto this part of the week. We have our first upcoming exam. It's directly a week away from today. It's going to involve just these sections right here. And truly, my pattern is it should only involve these sections. Why did 7.5 get thrown into the mix? It's because it's just a review section in its own right. It didn't actually have new material. We're just practicing random integrals in this section, which reviews the one in front. So I'm not directly asking questions out of 7.5. It's just that 7.5 is directly asking questions out of those sections. So it made sense. If this was, say, section 7.7, the first one we're doing for the week, that's the one that wouldn't have made it onto exam 1. So this section down here is going to be on exam 2. And as far as exam 1 goes, the information on the exam, the write-up is suggestion on calculators, just the basic scientific ones like we've suggested. And it is a closed book, closed note exam. But as you're studying for the exam, first thing you want to have open and ready to go is this. Not because I'm not going to provide it. It's the real last page of the actual exam 1. But if you're studying on the exam 1, you definitely want this in front of you because it'll inform you what's provided on the exam and which formulas that we have to be ready to go with for problems that could come up. So really, it's just kind of a listing of some of the important strategies, theorems, and definitions that we've gone through. And this is a formula, I guess, so it's good to call it a formula sheet. Integration by parts is one of the big techniques. 7.2 was strategies for evaluating these kind of combinations of trig functions, which means trigonometry comes up a lot in this course. And this is our unit circle diagram from right here. So this trig information will be provided for any trig evaluations that we have to do. This handles a trigonometric substitution aspect, section 7.3. And then below that is some pretty random integrals. These are ones that if they did come up in exam 1, I wouldn't want you to reinvestigate how to find this antiderivative tangent. This is one that was derived in Calculus 1. We should take advantage of it. And this stuff like these here, these are esoteric ones that derive in the first place. So if these come up, you're welcome to just use these as a catch-all statement of you're welcome to take them for granted. And our author did this one in section 7.1. So you don't have to keep on redoing integrate natural log x by parts because that's another one that just comes up so often. So this will be a selection of ready-to-go integrals that you can take advantage of and formulas that we saw. Pretty much that's how it's going to be for every exam. Just a write-up of some of the condensed version of the notes that we went through. Well, any questions so far, folks, about the exam, the formula sheet, calculators, or otherwise? Okay, then for the other exam materials down below, I have 3 versions of exercises, so it's kind of weird. We should introduce ourselves to them. I'm going to duplicate this on every single exam, including the final exam. So for version 1, these are lecture notes converted into worksheets. This is still pretty valuable stuff because unless you've memorized exactly how this one goes, it's a great one to practice. All I've done in these worksheets is I've taken out all the information about what the definitions are, the formulas, and so on. So you're really just going directly at the problem. If you can look at these again and solve them again, you're on great track in section 7.1. And it goes from a section by section basis. It's the same exact problems that we solved, so you can find the solutions by going up through here in those corresponding sections. Then sample exam 1 exercises version 2. I'm not sure if too many people take a look at these, but There's a reason it's here. It's my way to just indicate to you that when I write exam one, it's going to be heavily motivated by sample exam versions 1 and 2. In fact, after I write the exam, I double check these things. I check the things we did in class, that's version 1, the things that you did for homework, that's version 2, and I make sure my problems really fit there. That's not outrageously difficult, that it was actually something we looked at and tried out. So sure, these are your old homework problems, but way to use this document is if there's just one section that you felt like it was extra tricky, say section 7.3, then just go to 7.3 directly, try them again. I mean, you have solutions, you have feedback on this assignment. You can go through these again cold, then that's really great practice. Then, if you want some extra problems, that's version 3. Some of them are way challenging, and they would never make it to a real exam question, not even the final exam. But sometimes doing really hard problems is a great way to learn. So for folks that would like to take a look at that, that's version 3 down below. It has problems that have, occasionally a star on it, which is my way to say this one just became outrageously nasty. But there's a lot to learn in this 2-star, because if you look at that solution down below there, well, it's somewhere in there. Lots of good stuff actually happens. Let's take a look at 2-star. Well, it starts off awful. You start off by doing the trig substitution, then you have to do a U substitution, then you have to undo it all. It's an interesting practice. But again, these would not make it to a real exam setting. They're just a little too long, sometimes too technical, but great for studying. Think of it as an analogy. If you're going to run the Boston Marathon, you want to practice in really dry, hot, terrible conditions, because then when you go to the Boston Marathon, it's going to feel like a walk in the park. You've done the harder training, in other words. So that's the idea with version 3. Well, that's my announcements for introducing the first exam. Any questions at all, folks, about any of this information here? Okay, if questions do come up, don't hesitate to ask. We don't have an official review day built into our schedule, but if you do have questions that pertain to any review question or just things you'd like to take a look at the start of Thursday, I'd be happy to start class out that way. In fact, like we mentioned before, pretty much all class starts out with me saying, any questions from the class? That was a real question. Any questions at the moment? Okay, if we come back on, say, Wednesday's class, if you have a question on a homework exercise, a question on any of those review problems down below, those are always a great way to start off class. Even on Thursday, before we come back on Monday's exam, I'm willing to spend even a lot of time looking into questions if people have some they'd like to take a look at. But for what we're doing this week, finishing off section 7.5, which is kind of a way of reviewing on exam 1, that's kind of nice. Then we're going to look into some applications of what we've done. Approximate integration is another look into integration, where we'll look at midpoint rule, trapezoid rule, Simpson's rule. Then we'll do something technical with the so-called improper integrals before going to our big application chapter, chapter 8. So let's go back to 7.5. We ended up right here before we called it a weekend. And this one is section 7.4. That's the partial fraction decomposition theorem. I did not put that theorem on the formula sheet for the exam because that one's more about understand how the patterns go, less than reading the whole theorem and memorizing it verbatim. Oh, sorry, Jonah, I missed the question there. Jonah says, are you able to tell us if double and triple angle identities will be on the exam? Let's see here. I'm thinking they won't, but when weird trigonometric identities do make it onto the exam, I often bake it into the problem in this kind of way. Like how I said on section 7.5, exercise 19, this benefits from the double angle identity. I do that same thing on exams because I don't want you to stop demonstrating your knowledge of calculus just because you forgot one trigonometric identity. That's terrible. So I do actually solve my own exams, check for those kinds of things. And when it comes up, I do bake in these hints into the real exam itself. I don't think any major identities did come up from what I recall, though. Other questions at the moment? That was a great question. Thanks, Jonah. Okay, well, we left off here, partial fraction decomposition theorem. As far as the partial fraction decomposition theorem is going to go on the real exam one, you can absolutely expect a question similar to the first questions in 7.4, where all you're doing is writing down the form of the partial fraction decomposition, not solving for the coefficients. So that would be a problem on the real exam. And something like this, where it's controlled to be not too long, where we have to do the full process, is also going to be on exam one. So this one's a little bit harder, but practice here helps us with the real exam question. First thing to notice is, I don't know how to get a good u substitution working on this. So let's attack it directly by taking x divided by 2x plus 1 cubed and apply the partial fraction theorem. In the partial fraction theorem, this is case. Anyone spot what case this would be? It would be case 2, absolutely. Cases 3 and 4 are ruled out because 2x plus 1 is not an irreducible. That's a double negative. This one is nastier. This is the extra exercise that we added onto the notes. I did include any extra exercise on the actual homework assignment. Sorry for the confusion on that. But this will be our problem where we look into a case 4 situation. It's at least case 3 because x squared plus 1 is irreducible, but it's bona fide case 4 because that irreducible factor has been repeated twice due to that power 2. So that one's a little bit tougher. We'll just hide it for the moment. And work our ways towards it by navigating through this one, case 2 of the partial fraction theorem. So case 2 is not too bad. Here's what we do. We write down the 2x plus 1 once, the coefficient a above it. Then we need a new coefficient because we have to write this down 3 different times according to that power. Here it's to power 1. We raise it to power 2. Then we raise it to power 3 so that we're matching up this power here to here. If we could do that, that's the full decomposition for this one because there is really only one factor to the third power. Next step we take is clear all denominators. So 2x plus 1 cubed gets multiplied, cleared off on the left-hand side, and then visualize it, it merges here, here, and here, and we do a cancellation. You would get x equals a times 2x plus 1 squared plus b times just a 2x plus 1 to power 1. And then when we place it right here at the red dot, it's a full cancellation, and we just get plus c. So there's our polynomial on the left, polynomial on the right. And here's where a new idea comes in. It's not very easy to do the same strategy we used in 7.4 because only we have one great value to pick for x, -1/2. That only gives me one coefficient, leaving 2 more. And we'd have to pick other values for those, solve a system of linear equations. So sometimes another technique is preferable, and this is the case for doing that. We're going to use the method of equating coefficients. So we're using part D and the extra example part E as also another take in section 7.4. We solve those coefficients all in a particular way, picking key values for x. This is a whole new approach, which could work on those problems as well if you prefer. Here, it's probably the best idea or best advice for this kind of polynomial. So we'll start by just keeping the x on the left as before. We need to expand out these things if we're equating coefficients. So let's take a, expanding out 2x plus 1 squared gives us 4x squared plus 4x plus 1 after foiling that out, plus b times 2x plus 1 plus c. Could have distributed here, but let's do all of our distributions on this next step. So we have 4a x squared. I'm distributing a in, but you want to think of A as a coefficient going in front of the x squared. We're organizing this more based off the power of x's that we see. So the next one should be written as 4ax plus a plus, now from over here, 2bx plus b plus c. Okay, now that we have that down, we should say what the punchline is in the first place when we're using the method of equating coefficients. So the idea here is that two polynomials are equal if and only if their coefficients, that was going to color code, but that's going to look weird. I'll stick to this color. If their coefficients are equal. So that's the idea of this whole method right here. There's a polynomial on the left, there's a polynomial on the right. The polynomial on the left is degree 1. That forces the polynomial on the right to be degree 1. Already, that means a is 0. But to do this in a more organized way, here's what we're going to do. If x squared comes into play, we're going to write the left-hand side with the power of x to power 2 and go 0x squared plus, instead of x, let me write this in as 1 times x, because this is all about the coefficients. We need to display them. Then there's a constant term. It just happened to be 0. So that's the entire left-hand side written more complicatedly. But now we compare that against the right-hand side. What goes with x squared? It's just this 4a x squared here. So that means 0 corresponds to 4a, and that's a whole new equation. Then let's do it again. We have 4ax, 2bx. Factor out x from both of those to get plus 4a plus 2b x. Then from here, we have a coefficient of 1, which must be equal to the coefficient 4a plus 2b. That's the only way this polynomial is truly equal. Next, we take all of our constants here. There's a, b, and c. Let's go plus, in parentheses, just so we can associate them as one thing, the constant coefficients, a plus b plus c. Now, a plus b plus c is the constant term of the polynomial. It must be directly equal to this constant term on the left-hand side. So we've equated coefficients, and this now produces 3 equations. Starting with the color coding, we have 0 is 4a is equal to 4a. Almost said x squared, just the coefficients that we were equating. Next, go to coefficient 1. It has to be equal to 4a plus 2b. And last one. The constant term is 0. So it equates with this constant term, a plus b plus c. So we have 3 equations. If we can solve these in an efficient way, then equating coefficients is a valid technique. Sometimes it's more work, like in the homework section where picking x equals 0, x equals -2, that is actually faster in a lot of situations when you have great key values for x. But when you're lacking them, this method starts to become the preferable one. And look how fast it is. 0 equals 4a, we already have a solution. A is 0. We can substitute that here. 1 equals 4 times 0 plus 2b. That means 1/2 equals b. That's our second coefficient. Over here, we have 2 values now. 0 equals 0 for a plus 1/2 for b plus c. This implies -1/2 equals c. So now we have all of our coefficients all set up. We'll just drop them right up in here and integrate. Let's see, that was a definite integral. It's easy to forget in these problems. So this is now the point at which we can return to the original question and actually integrate it. But this is most of the work here, pretty much. Any questions at all, folks, on getting those A, B, C coefficients? Okay, so last step. With a lot of steps in calculus, it's just substitutions. Go up here. Let me try again with the pen tool. Go back up here, and first term is gone. We don't need to write it in if 0 is in the numerator. We'll just scoot over to this one. B coefficient is a 1/2, so that is 1/2. 2x plus 1 squared. C coefficient is a negative 1/2. Two x plus 1 cubed. And I keep forgetting this is a definite integral. We need to evaluate this from 0 to 1, and then we'll be home free. So that's where the new problem comes into play. It's kind of an awkward integral to do because of the base 2x plus 1 being the denominator in both terms. So I'll do this optional step. This just helps me see the antiderivative a lot faster to write this in as 1/2. Leaving that in the numerator, bring this base up to write it as 2x plus 1 power negative 2. Then another negative 1/2 multiplies base 2x plus 1 power negative 3 dx. I might claim this integral is way easier than this one, even though it's the same thing. It's just all about how you visualize it. So let's try out this one here. First thing I'll do is carry down the constant 1/2. Then come over here and put in a little bit of space before we write in 2x plus 1 to its new power, which goes up by 1, so it's a negative 1, which means we come over here, multiply by the reciprocal of negative 1, and just so that the chain rule doesn't cause any issues, we also have to multiply by the reciprocal of that coefficient, so times 1/2. So this gives us the full antiderivative from right here, but this is really just one way of doing it. Does that make sense on how we got it to this step? Okay, the really fast scratch work visualization, I'll delete this in a moment, would be if you differentiated this, you would get 1/2. Here I'll just call this a negative 1/2, simplifying it, times 1/2. But now when you differentiate this, you get an extra negative sign. Power goes down by 1, so it's negative 2. 2x plus 1 goes inside. Chain rule says multiply by the derivative of 2x plus 1, which is times 2. So we have negatives killing each other off. We have 2 killing off 1/2. This whole thing would then be 1/2 times 2x plus 1 power negative 2, which is what we started with up here. So this is one way to do it. This is just a check to show how it goes. Sometimes the check shows what the pattern is on getting that extra 2. The second way of doing this is really it's just a U substitution process to get that down right a second way. Anyone want to see it done the U substitution way just for the sake of practice? Awesome, let's give that a try. I always encourage these shortcuts whenever it's a U substitution, but the function is linear. But sometimes that is confusing. It's good to see it two ways. The standard way is more robust on an examination. So if you're well practiced in doing it that way, that's a good call as well. So if I was doing this from scratch, no trickery like we did over here, we would say integrate. Let's just put the half there. 2x plus 1 power negative 2 dx. The u in the u substitution is just the inner function, 2x plus 1. We need a differential, which would be 2 dx. Next, we can we can solve for the dx and write 1/2 du equals dx, which makes sense. Now we're just making a full replacement of that dx there. And then this turns into equals 1/2. Integrate u power negative 2 times, forgot my 1/2, I'll put it inside the integral, 1/2 du. So we see where this 1/2 came from, and this 1/2 came from. This one was just copied in. This is through the chain rule, or through this differential, if you're going through this process. Oh, thank goodness. More space is not always easy to get on this stuff. So we would get now 1/4 multiplying the halves together, u power -1 plus a constant. We have to divide by that -1 or just multiply by -1. We have -1/4 here as well, and then it becomes -1/4, 2x plus 1, power -1. So, oh, and a constant if it was indefinite like we indicated here. So this is a way to do it through the u substitution method. But again, it's good to be really confident with this procedure whenever it comes up. But you'll notice if you're doing tons of these problems because you're studying Calculus 2, this is just as valuable. It's going to allow you to focus on the main concepts of the calculus and not get bogged down too deeply on u substitution every single time. So it really is valuable to see it both ways. Either case, we're off to the next one, -1/2. Trying out this method again, where we skip the u substitution and just put in the right values, here's how this one would go. Put in the 2x plus 1 base a little bit further to the right. The new power goes up to a -2. Then when you're over here, we have to divide by the reciprocal of that new power. Excuse me, multiply by the reciprocal of that new power. So here's 1 over -2. But if we check our answer through the chain rule, that 2 causes problems. We counteract the 2 causing problems by just going times 1/2. So that times 1/2 there meant we didn't have to do that 2 times. Again, it saves you a lot of time in writing these things down and getting your antiderivatives. But then the next thing is this whole thing is evaluated from 0 to 1, so those are our next steps. Any questions with this core step here, though, getting the antiderivative? Okay, so it's a bit of a mess. I wouldn't want to do the evaluation really if it looks like that. Let's simplify first and then evaluate it. It's a lot less writing that way. So this now becomes, from here, we have a -1/4. And let's write this in a slightly different way. -1/4 times 2x plus 1. Because we're actually doing an evaluation, I think it's a good call to simplify this, forcing in the positive exponent. This, let's see, count the negative signs. It's a plus 1, let me try the same strategy here. 1 over 8 times 2x plus 1 squared, evaluated from 0 to 1. Now that's a little bit easier to do, to actually get the values out. Now for upper limit of 1, we would get here, let's see, that's just 4 by 3 in the denominator. So -1/12. This one's a little bit more annoying. Plug a 1 here, that's 8 times 9, so 1 over 72. Minus, now we're using lower limit of 0. 0 here is just going to give us -1/4. That's kind of nice. Plus 0 here gives us, let's see here, that's 4 by 8. So that's positive 1 over 32. And we're just about there, folks. That's not too bad so far. But because we're getting closer to exam 1, I did want to make one comment about exam 1 as it relates to this kind of stuff. When you see this kind of stuff in an exam setting, this is an acceptable answer on any exam. Exam 1, the final exam, and so on. And there's a reason for that, because really right here, once you went beyond the evaluation, the calculus stops. I don't have any concept that I really want to take off points just based off ordinary arithmetic. I know you can work this out by hand, and I know you could put this into a calculator like Desmos TI-84, get a fast operation. So it's not as big of a deal on an exam. If I saw you did all the calculus just right, but ended at a whole bunch of fraction arithmetic, I'll just assume you decide to go to the next question and demonstrate your calculus understanding there, rather than spinning your wheels on this kind of stuff. Only thing to watch out for is, be sure on exams, this part is important mainly because trig and exams, there's always expectation to do evaluations. So be sure on exams to always evaluate things like cosine pi over 2 when it comes up, we should just say 0. Sine pi over 6 when it comes up, we should just say 1/2, etc., etc. But then if you have a bunch of zeros, 1/2, minus 1/8, if you stopped right there, again, that's a decent stopping point. Let me double check. Could have been a mistake. So I plugged 0 here for x. So that means that was 2 squared. So 8 by 4. That's how I got that 32. It was really just that power 2 making the numbers kind of unsavory. Other questions so far? Okay, I guess my question for class then is, should we work it out just for the fun of it by hand, or would you rather a calculator? With no one mentioning anything, let's go with the comments we made in spirit over here about this. Let's put this in a calculator and then just focus on the calculus on the next problem. Because again, arithmetic is never the main thrust of this class. It's still important to get exact answers, but that is an exact answer for an exam. Yeah, go ahead. Yeah. Oh, yeah, that's weird. Why did I think 32? Yeah, that should have been plus 1/8. 0 went into that location. Thanks for spotting that, folks. That should have been a plus 1/8. That deserves some highlighting there. Arithmetic, again, is kind of nasty sometimes. And that's unfortunate because I do consider this part as being part of the calculus. We do have to do the evaluations, right, to get to that level. So good for spotting that one. That could have been a -1 point or minus a half a point for making that mistake there. But other questions at the moment? Okay, let's plug this in, get a number, and we'll move on to the next integration. So plus 1 over 72 minus, with the better numbers, negative 1/4 plus 1/8. Okay, so we've got decimal value. We want a fraction, but clicking on that will reveal it was just 1/18 all along. Let me double check. Well, I put in a parentheses though to kind of group them together. Oh. Basically, I just typed it in verbatim. I kind of saved some steps that way. Other questions so far? Okay, throwing that all in, we get a 1/18. And even though the TID4 calculator is not allowed on exam 1, if you use those calculators just in your personal work, here's a way to get the fraction out as well on that kind of calculator. Go, let me get out of this mode. Negative 1/12 plus 1 divided by 72 minus, I'll do that lazy way of just typing this in verbatim, negative 1/4 plus 1/8. Close the parentheses, hit enter. And then if you need to convert this to a fraction, hit the math button. It makes sense, right? And the first option that TID4 decided you're probably going to use is convert to fraction. So just hit enter right here. And that's one way to do it in these kind of calculators. Pretty much every calculator has a way to do that, even this one, but it just gets trickier and trickier the less features your calculator has. Well, any last questions, folks, on getting through this problem? Okay, well, let's try out one more then. Here's the last one for this section before we turn it over to approximate integration. This is the bonus problem, and its existence is only because we talked about case 4. We did decompositions that we didn't fully solve on case 4. So we might as well do one top to bottom problem on case 4. This is that problem. And it's not as crazy as it could be. There's just one irreducible. X squared plus 1, it's been repeated. That's what makes it case 4. So first thing to do here is decompose. X cubed divided by x squared plus 1 squared equals, this is all about the patterns. So the moment you see if something that's been repeated, like this one, start by writing in x squared plus 1, then x squared plus 1 squared, since we have to build up to whatever that power 2 or whatever that power happened to be. If that was power 5, we would have 5 terms ending at x squared plus 1 to the 5th power. But other thing to watch out for is, because that's irreducible, numerator is different on this one. Anyone recall how these go? Good call. So ax plus b on the first one, like you said. And same one on the next, cx plus d. So that's our setup so far. If we can solve for all coefficients, we'll be on our way. So let's see what happens on this one. First thing we want to do is clear denominators. So left-hand side is x cubed. All of this multiplies over here. And when that happens, we get ax plus b multiplying x squared plus 1. So there's just one power canceled off on that one. But when we multiply it way over to here, it's a full-on cancellation. So all that's left off is cx plus d. So that's what it looks like to clear the denominators. Any questions to this stage? Okay, now there's two approaches. You could pick 4 numbers on here, but if you did that, you would have 4 different equations in the 4 unknowns. It's a really tough problem to solve that without extra tools like linear algebra to solve that system of equations. So again, we'll just use the method of equating coefficients, which starts off by expand the right-hand side. So here we'll be foiling, so ax by x squared gives us ax cubed, then plus a ax, distribute b through to get plus bx squared plus b. Now we're just copying plus cx plus d. So we have degree 3 polynomial on the left, a degree 3 on the right. What we'll do is really exhibit the coefficients we're exhibiting by writing the left-hand side in a weird way. 1 by x cubed plus 0x squared plus 0x plus 0 is the way to write the left-hand side. On the right-hand side, we try to organize as much as possible, starting with ax cubed. Now we need to find our squares, just one of them, plus bx squared. Next, we need to find our linear terms. That's the ax and the cx, but factor x out from to the right to get a plus c x. Last is the constant terms. We consolidate them all into one grouping. It's b plus d. So now we have really 4 equations here. Sure, it's just a polynomial, but if you set a polynomial equality like this, we're also saying that 1 equals a, 0 equals b, this 0 equals a plus c, and I ran out of colors, but this 0 equals to b plus d. So 4 immediate equations, some of which solve our system or solve our coefficients as we go. So from here we have 1 equals a. Down the line, for the x squared terms, we have 0 equals b. Now for this one, 0 equals a plus c, but we can also substitute information. We knew the value of a, so we can say 0 equals 1 plus c. That solves c. It's -1 now. And now last, we're taking this coefficient 0, set it equal to coefficients b plus d. I'll just use that purple line to convey that these both went together in that way. What do we have here? B. Oh, we have a value for b, thank goodness. Because if we didn't have something here for one variable or the other, we're stuck again. If there's 2 unknowns, you need 2 equations. But that's the other equation. So we'll throw 0 in for b right there. 0 equals 0 plus d. That means we have a value for d. Nice to see those zeros. So this problem has been obviously rigged to be as nice as possible, but we're getting through it, folks. We now have the coefficients, so we can integrate on the next steps. Any questions at all, folks, getting through these main results here? Okay, now to summarize, we're taking antiderivative x cubed divided by x squared plus 1 squared. But by the algebra above, this transforms into something much nicer. Let's take a look. We're putting in a 1 for a up here, but the b coefficient goes to 0. So this whole thing is just x. Let me try again there. This whole thing plugging in a and b gives us just x divided by x squared plus 1. Then over here, c is a negative 1, d is 0. So this whole thing can be rewritten as negative x over x squared plus 1 squared dx. So now if we can solve this right here, we're on our way. Any questions at all, folks, to get to that stage, the major substitution? Okay, looking at these, they look like they're both U substitution techniques. And we've mentioned a lot of times that you should consider the shortcuts when it comes to U substitution. But for me personally, when I start to see stuff like this, I usually would do the U substitution. So let's take our time with this one and rewrite this as it's two integrals really that we can break up, and which is a good call because it's going to take different substitutions. Well, is it? Not really, but let's break it up anyways. Let's integrate x over x squared plus 1 dx minus x over x squared plus 1 squared dx. Again, it looks like the same substitution is going to work on both. That's kind of nice, unexpected. Let's pick u is x squared plus 1. Then the differential of u should be du is 2x dx. Our standard trick here, whenever a coefficient like 2 comes up that we don't know what to do with, is often go a half du is x dx. Now for both of these integrals, we can replace x dx in a nice way. A half is just going to go in front, and dx transforms to du. We'll have a u here, a u squared here, and now we're ready to just do both substitutions at once. So for this first integral, we have 1/2 integrate 1 over u du. Then same game on this one. Extra negative sign is the only difference, 1/2. Well, there's another difference. Integrate 1 over u squared du. And that's very obtainable integrals. So we'll be able to solve both, undo the substitution on both, and this one is indefinite. We'll end the problem right at that step. Any questions to this stage so far? Okay, let's write this out. Going left to right, this is 1/2 natural log absolute value of u. On this one, I usually don't really look at that. What I do in my mental blackboard, which I'm not very great at, I usually have to write it down to see it, but I view this as u power negative 2 du, so that I get negative u power negative 1 and a constant, or negative 1 over u plus a constant. I usually never consider the power rule with a base in the denominator. It just messes with my head on what's going up, what's going down with the powers. So for this whole thing, view it like this, and we're really looking at minus 1/2 multiplied by negative 1 over u plus a constant. So all we need to do is undo these substitutions, 2 of them, and the problem has been satisfied. Well, we have an antiderivative. So we have 1/2 natural logarithm. U is a non-negative function, so follow whichever stylistic way you'd like to format it. For me, whenever I have something non-negative, I usually think of this as a small simplification and put in x squared plus 1. Oops, sorry, with the random scrolling. I'm trying to hit Control Z, which does random things sometimes. Then minus 1/2. Actually, let's simplify that down a little bit better. This is plus 1/2. And in place of u, x squared plus 1. And add the constant. So my claim is if you differentiate this line, you get up to this step, and then add the fractions, you would get back to this step. Adding the fractions is just the reversal of the partial fraction decomposition theorem. It's weird how sometimes going one direction is easier, subtracting those two fractions, but breaking them apart is a whole big process in and to itself. But any questions at all, folks, with the conclusion here? Sorry for this holding on that, but I think I'm on the end of the document. I didn't know there's a cursor space right here. Well, we did it, folks. Again, think of section 7.5, especially when you do the homework questions in there, as just random extra practice with integrals, where it's selecting problems pretty equally and randomly from section 7.1 through 7.4. Oh, let me finish that. So we're pretty much through all the content that you're going to see on the very first exam. Next, we're going into section 7.7. Our schedule's pretty tight, so we keep on going, but we'll never try to rush through any of these sections. That's the one thing that is the worst when you're trying to learn mathematics. So section 7.7 is our approximate integration section, but also gives us a good chance to kind of pause and think about what is it that we've been doing anytime we've done a definite integral. We've done one today at least. And so if we're thinking about approximation, that means we're just doing more of those definite integrals, but now a class of really hard problems. Before we describe all these things, let's explain why we need approximate integration. Let's put it down on the margin right here, maybe. So the reason for all these fancy rules is that when it comes to integration, it's actually a pretty hard problem. Think of the problem, for example, of differentiation being no different than doing something like this. Doesn't matter how bad my multiplication goes here, getting the answer is immediate. Think of integration as the reversal of all this. Starting with a number, a very large number like this, what are its factors? What are all of its prime factors? That's integration. It's a wildly hard technique, it turns out. Whereas if you're differentiating something, we have plenty of rules that tells you exactly how it goes for whatever the function is. And here is a really hard integral problem. Antiderivative e to the x squared. And this is not like some esoteric type of antiderivative problem. This comes up in applications that we're going to see in chapter 8 with really simple systems of circuits or population dynamics along with differential equations. That comes up out of a really reasonable problem, something fantastically abstract. Our author says this has no elementary antiderivative written in closed form. But it has an antiderivative. What this comment is saying here, no elementary antiderivative in closed form, is take all of the operators that we know so well, add, subtract, multiply, divide, exponentiate, logarithms, square roots, take all of it, put all those together with any number whatsoever, any symbol, variable whatsoever. You cannot write down the antiderivative with that stuff unless you use infinitely many of those operations and operators. So that's really bizarre. That's part of why we're going to go into chapter 11, look into power series, Taylor series, Maclaurin series, to get a better feel for, well, if it's not an elementary antiderivative written in closed form, what form does it have? Polar form, let me think about that. Yeah, you could convert this into polar form to come up with an antiderivative. But another form it could have is something like this. For example, e to the x is a summation as you go from 0 to infinity of something along the lines of x divided by n factorial. Or hang on, let me go. Forgot how that goes. Hang on. Let me give these self. I'm going for the Taylor series of e to the x. That should have been an easy one to remember. Somehow I forgot. Let's see what they say here. X to the n. That's where I was messing up on that one. So that should have been x power n. Apparently I'm a little foggy on that too, but these are the things we're going to get into in chapter 11. So if you can bring this into the table over here, you can get an answer. And it's an okay answer because you can approximate this really, really fast. Again, we'll call this a chapter 11 content. This one is a Taylor series. But still, we can give an answer to this even before Taylor series. For example, you could say an antiderivative is take integral e to the x squared dx. We're going to use the fundamental theorem of calculus part 1. That's the weird one. Part 1 says there is always an antiderivative as long as this function is continuous, and it is. Antiderivative goes integrate from 0 to x e to the power t squared dt. We do a change of variable so there's not a conflict with the upper limit of notation and the variable in the integrand, and add c. So if you just need to work with this, if it showed up in your problem and need to get a handle on it, that's an antiderivative already. Notice the problem though. How do you evaluate this antiderivative at like x is 5? You still have to use a midpoint rule or say a left endpoint approximation, right endpoint approximation. It's still a tough problem. So that's what chapter 11 is trying to do. Give a slightly better answer than that, which is more useful, more computational, instead of having to resort to the fundamental theorem of calculus part 1 and use approximate integration on that output there. But it's good to know you can at least give some answer to this. So this is the reason why we like approximate integration. Then this part of the notes up here is just us getting started, recalling some things from calculus 1 before we start writing down what the formulas are going to be. But any last questions or comments, folks, with kind of the reason why we're here stuff down below? Okay, well, aside from this stuff, let's recall what we mean by the definite integral in the very first place. First, this is a great theorem. It tells us when you can integrate something. If your function is continuous on a closed domain, then it's automatically integrable. And these are the major functions that we work with most often. But integration is extremely technical. There are other cases our author mentions. If it has a finite number of jump discontinuities, you could still integrate it. You just break up your integral across those discontinuities. So if it has a jump at c, integrate from a to c, integrate from c to b, and you're all set. So aside from that technicality, let's assume our function f is just an ordinary continuous function on the closed interval from a to b. Here's what the picture could look like. Let's say this is our a, just so the picture is mostly in quadrants 1, 4, making it a little easier to look at. Here's b, for the integrand f of x. Let's say it starts up here and then does this kind of little decrease down to that level once we get to b. So we would like to integrate that function. We say integrate from a to b to refer to the signed area under the curve. It's going to be mostly positive because of this region being greater in area than this region visually. But to make this happen, we do a partition into n subintervals equal with delta x over n. So really our first operation in doing this is to calculate delta x. We take the upper limit of integration, b, minus the lower limit of integration, a, divide by n, and that's just going to be the equal widths of all the rectangles we're going to build out. So next step, we say a is x naught, the distance from here to here is meant to be a distance delta x. So going from here to here, delta x, every time you write down those tick marks, even if it doesn't look great on the picture, just use your imagination. It's intended to be the same width. This will be x1. That'll be x2. That'll be x3. And again, pretend that's equal width right here. This b would be x4. So this is a picture when n is exactly 4. Really, when we do integration and we want a great approximation, we want 4 to become 4,000, 4 million. But what we really want to do is put a limit on n to make the number of rectangles go to infinity, making their widths go to 0. And if the function was continuous on that closed interval, this really has an answer. It's a tough limit, but let's draw it out at least to get a visual on it. So we've done the part where we partition the interval into n subintervals equal with delta n. The next thing that's kind of weird here is the sample points, x1 star through xn star. They could be anything whatsoever. They just have to be between each one of these intervals, is what's mentioning here. So let's pick out some xi stars. First one could be right here. Because it's midway between a and x1, we might call it a midpoint. This one is just a random looking one. Here's x2 star. For the next one, it could be exactly equal to x3, the right endpoint, exactly equal to x2, a left endpoint. Makes my picture look a little crazy, so I'll put it over here to make it readable. Let's say x3 star is way over here. And just to emphasize it can be a right endpoint, let's let this one be x4 star. So right on this tick mark. After we do that, more things happen to the diagram. The function itself, the integrand, is going to determine the heights along with the sample points. So x1 star would go directly up to hit this value. This would be f at x1 star. It implies that we have a rectangle now that goes like that. In the Riemann sum, that would be this one. That's just the area of the first approximating rectangle. Then we go off to the next, all the way to the end. And again, this is the picture where n is 4. So let's draw in the rest for completion's sake. x2 star gives us a value right up here. So our rectangle goes like that. But the moment we get to the x3 star now, things are changing. At x3 star, our function value is down here. That gives us a negative quantity, f at x3 star. That one's negative, whereas these are positive. And that's the reason why we say that this region gives us positive area, just because the function values used right here would be positive. But the curve is below, our function values are going here and here, suddenly become negative now. So that's how we were getting signed area out of the definite integral. So this rectangle here, just for finishing off the visualization, would go through here. Picture starts to get a little bit busy, so it's more valuable to build out the picture rather than looking at the whole thing completed. That's hard to look at. But for the last one, if it's a right endpoint, this rectangle goes like this. So that will give you the result of that summation here. It's a very crude approximation of the signed area. So the only thing that fixes it is not putting a large number there necessarily. It's more about throw a limit in front of it. Now we say we have a limit of a Riemann sum. And because we have conditions on f through continuity, this limit would really exist. And we'll just say that that's the value of the definite integral down here. So that's the kind of things that we're going to be doing. And with approximate integration, all we're doing now is deleting that and saying approximately equal, and maybe using some kind of reasonable way to select these sample points so that they're not in random locations, and we can build out a formula more rapidly. So that's just a quick rundown of what we've been doing all along for the definite integrals and what we're about to do with our approximations. Any questions at all, folks, with the diagram? Forgot that last part there. Okay, well, let's try this out then on a problem which is probably familiar. The midpoint rule. This one's just kind of a tie-in from what we did back in Calculus 1, but we won't really see this one on exams too often. Well, probably not a lot, or let me say not at all. This midpoint rule will come up in the homework because it's a good one just to get practice in before you're doing the other rules. But also watch out for the way the homework has been written. Exercise 7 is actually really, really long and it's fantastically tedious. It's going to feel like busy work. But all I'm asking you to do on this exercise is strictly part A. It means it's probably just the midpoint rule. This one, I just want you to do, it's probably just the trapezoid rule on that one. Just use Simpson's rule on this one and so on. So this exercise set is not to be meant to be that long, but it can be. Just watch out for these parts right here. Same for this one. Let's try this out with the midpoint rule and see if we can get a value out. Well, let's maybe start the midpoint rule on here. I'm not sure if I want to run through this in about 5 minutes. Usually these are good 10-minute problems. Let's see the steps you would take. If we were going to solve this one or get it set up for when we come back on class next time, here's how I'd probably start each and every time. I would say this is approximately equal to M4. M because we're using the midpoint rule, 4 because we're using it with n equals 4. Next thing I would do is just write down the formula for M4. It goes, you can consult the information above, delta x multiplying f at x bar 1 plus f at x bar 2, f at x bar 3, f at x bar 4, and that's the whole formula. Once we have that formula down, the next most important thing, in my opinion, is get your delta x written out. So let's call this step 1. Step 2, we need our value for delta x because, I mean, it goes there. It also tells us what x bar 1 and so on ought to be as well. We just go up here, do b minus a, divide by n, evaluate it at 2 minus 0, divide by 4, and either the fraction is fine or the decimal is fine. I'd say just go for whichever looks like it's going to be easiest. This is an approximation problem, and all the problems on this entire homework set will be to approximate. So I'll go with the decimal value. It's easier to write in. And this means for step 3, we want to find the midpoint. Here's how we do it. It's literally this. You can take x0 plus x1 divided by 2, and you've got a midpoint. But sometimes these are kind of clunky to work with. And the author, this is typed out verbatim, the author seems to suggest that you need to do this 4 times, which is kind of not a best strategy. If you are not a fan of working as hard as possible, here's a more reasonable way to do this. Write down x0. Anyone see what x0 is in this problem? Absolutely. It's always the lower limit of integration here. Now, instead of averaging things, I just want to go midway between x0 and the next value, x1. The way we do that each and every time is go x0 plus, well, delta x will take you to x1, go halfway, and you're going literally to the midpoint now. So x bar 1 is 0 here, plus 0.5 divided by 2, which finally tells us x bar 1 is just 0.25. So that gives us this value here, but actually it gives us all of the values. This one is 0.25, and we should be able to guess this one. Well, not really guess, it's an informed result. Anyone see what it should be? Exactly. We just take our delta x, add it over each and every time. So this will be 0.75 like you said. Do it again, add delta x, which is a 0.5, and we're at 1.25. Do it again, add 0.5 to that, and we're at 1.75. And notice we're half a delta x, 0.25, away from the upper limit of 2. That gives us evidence that we do have the right values. Well, that's the setup to all this. The next thing we have to do is actually plug this in, throw it into a calculator, get a value out. But this is the setup to any one of these midpoint rules. Any questions at all, folks, on just the setup portion? Okay, sorry for basically going right up to the minute on this. I don't think we're gonna ever try to rush these in 2 minutes, but we talked about approximate integration. I felt like we had to end on what a setup could look like. When we come back on Wednesday's class, we'll finish off the midpoint rule, but then pay more attention to the trapezoid rule and the Simpsons rule. Those are going to be the main things that we'd be tested on upcoming exams. But have a great night, folks. Drive safe. I'll see you all on Wednesday's class. Thank you.
Thank you.
Awesome. It was just that
Yeah.
start. Awesome.
It made it so simple.
Gotcha. It's always crazy how with one small mistake, you can get like right up to the right answer though. Yeah. Thanks. Any questions?
Can I turn in the?
Yeah, that'd be just fine.
My
To be totally honest, I only grade assignments on Fridays anyway, so that's always totally
My
reasonable.
basement flooded today.
Oh no, I'm sorry. I've got a basement too. That's rough. That's one of the reasons I hate spring, to be honest.
Yeah. Well, we don't even know what caused it.
Yeah,
Yeah,
dang it.
there's no leak, the ones we're gonna find out, it just happened.
That's even more mysterious.
Yeah.
Well, I hope you get a handle on that.
Probably gonna happen again.
Yeah, yeah.